Welcome to AI Paper Slop, our YouTube series where we summarize the latest AI and tech papers. We are diving straight into today's paper.
Let's do it.
It's called DiffusionOPD, a unified perspective of on-policy distillation in diffusion models.
Fresh out of Fudan University and Alibaba Group.
Exactly. And look, if you are out there optimizing diffusion models, here's the 60-second TLDR of this deep dive.
The bottom line up front.
Right. So reinforcement learning works incredibly well for pushing a diffusion model on a single task, like generating beautiful aesthetics or rendering perfect text.
Their single tasks are easy.
But when you try to optimize multiple tasks simultaneously, the model just breaks down. You get severe gradient conflicts or catastrophic forgetting.
Oh, absolutely. It's a nightmare.
So this paper proposes a two-stage solution. Stage 1, train task-specific teacher models completely independently.
Okay.
Stage 2, you distill all their distinct capabilities into a single unified student model using on-policy distillation, or OPD.
And that's where the magic happens.
Yeah, the real technical hook here is that they take this OPD framework from discrete LLM tokens and lift it over to continuous state Markov chains.
Which is mathematically wild.
It is. They derive a closed form per step KL divergence objective, and that drastically reduces gradient variance compared to standard PPO.
Right.
Plus, it works with deterministic ODE samplers, and it basically crushes the multitask baselines.
It really does.
Yeah.
And, to truly grasp why this specific architecture is necessary, we have to look at the massive bottleneck you've likely faced if you're an ML engineer building one of these God models.
Right, the one model to rule them all.
Exactly, because we all know the end goal, right? Users don't want a pipeline of 5 different specialized models.
No, they want one single box.
Right. They want one model that adheres perfectly to complex prompts, renders flawless text, and, makes it all look aesthetically stunning.
But trying to train a model to do all 3 of those things at the exact same time is notoriously difficult.
Oh, it's brutal.
The first standard paradigm most teams try is joint optimization. You just throw all your reward signals.
The OCR reward, the aesthetic reward.
Yeah, the composition reward. You just dump them all into the loss function and try to optimize them simultaneously.
Which almost immediately leads to objective conflict.
Right.
The gradients for these different tasks literally start pulling the model weights in opposing directions.
Because they're fighting each other.
Exactly.
Yeah.
You're asking the model to update its parameters to make the text sharper.
Okay.
Right? But that specific parameter update might ruin the delicate lighting the aesthetic reward is trying to achieve.
And compounding that is task difficulty imbalance.
Right.
Let's actually unpack that for a second.
Yep.
How does task difficulty warp the optimization?
Well, think about the density of the reward signal. Improving basic aesthetics is a relatively easy gradient to follow.
Sure.
The model quickly learns that adding more contrast or smoothing out textures gives it a higher aesthetic score.
It's a dense signal.
Exactly. But compositional alignment, figuring out how to render a zebra underneath the piece of broccoli.
Which is a real prompt from the paper.
Yes. That is a sparse, highly complex reward landscape. So the easier aesthetic task just dominates the learning dynamics.
It hoovers up all the optimization bandwidth.
Right, and the signals from the harder tasks are just completely suppressed. So the model basically just learns to make pretty but structurally inaccurate images.
It's like trying to learn to juggle, ride a unicycle, and recite Shakespeare all at the exact same time. You just end up failing at all of them.
That's a perfect analogy. Just fall off the unicycle.
So if joint optimization results in the model essentially giving up on the hard tasks, teams usually pivot to the other paradigm, which is Cascade RL.
Sequential training.
Right. You train on the text rendering dataset, you get the model good at that, you freeze it, and then you train on the aesthetics dataset.
But then you run straight into catastrophic forgetting.
Right. You learn the Shakespeare sonnet, but you instantly forget how to juggle.
Exactly. Because as you update the weights to learn the new task, you physically overwrite the representations that were crucial for the previous task.
So by the time you finish training for aesthetics, your model has completely forgotten how to spell.
Yep. And to mitigate this, baselines like Cascade NFT require these incredibly complex learning rate schedules, multiple distinct training stages, and honestly, hyperparameter tuning that feels more like alchemy than engineering.
It's absolute guess and check, which brings us to the central question. If both joint optimization and Cascade RL fail because of these inherent gradient conflicts,
Right.
how does throwing distillation into the mix actually fix the core problem? Because even in a distillation setup, we still have multiple conflicting rewards we want the student model to learn, right?
We do, but the brilliance of DiffusionOPD is that they don't try to solve the gradient conflict within a single training run.
Yeah.
They solve it by structurally decoupling the problem into two distinct physical stages: exploration and integration. In stage one, you completely isolate the tasks. You don't train one model to do everything. You start with a base model. The authors use SD 3.5 medium for this, and you train separate, highly specialized teachers using standard, off-the-shelf RL.
So you let the model specialize without any crosstalk whatsoever.
None at all.
Looking at their setup, they train a GenEval teacher specifically for compositional alignment using that diffusion NFT algorithm.
Right.
And then they train an OCR teacher for text rendering and an aesthetic teacher using the GRPO guard algorithm.
Yes. And because they are trained independently, there is zero cross-task interference. The aesthetic gradients aren't fighting the OCR gradients.
Right, because they're literally different models at this point.
Exactly. Each teacher becomes a pure expert in its narrow domain. Then, and only then, do we move to stage two, which is the multitask on-policy distillation.
Okay, so how does that work?
Well, you initialize a unified student model from that same SD 3.5 medium base, and the student starts rolling out its own generation trajectories.
That's the on-policy part.
Exactly. It's actively steering through the denoising process.
Yeah.
And for every single step, you bring in those specialized teachers to provide dense supervision.
So at time step T, the student looks at its current noisy latent state and essentially queries the experts.
Right.
It asks the GenEval teacher, like, what is the optimal move here for composition? And it asks the OCR teacher, what is the optimal move here for text?
Yes. The teachers calculate what their optimal velocity or transition would be at that exact latent state.
Okay.
And then the student updates its parameters to minimize the distance between his own proposed transition and the average of the expert's transitions.
Okay, wait, let me push back on this architecture for a second. So,
Sure.
generating on-policy rollouts for every single step of a student model's update sounds incredibly computationally expensive.
It's definitely not free.
If we have these three amazing perfect teacher models, why are we forcing the student to generate its own noise trajectories during training? Like, why not just batch generate 10 million perfect images from the teachers offline and then run standard supervised fine-tuning SFT on that massive data set? It avoids the overhead of on-policy generation entirely.
It's a totally valid objection, and the authors actually benchmark directly against offline SFT, as well as other distillation baselines like DMD or distribution matching distillation. The fundamental flaw with offline SFT is that it only exposes the student to the happy path.
The happy path, meaning the perfect error-free trajectory.
Exactly. When a teacher generates an image, it stays within a very narrow high-reward manifold of the latent space.
Right.
If you train the student exclusively on those pristine trajectories, the student learns what to do when everything is going perfectly. But what happens during inference when the student makes a tiny suboptimal prediction at, say, time step 900?
The latent state shifts slightly outside that perfect manifold.
Right. And because the student has never seen that out of distribution state during SFT training,
It completely freaks out.
it doesn't know how to recover. The error compounds at time step 899, then 898, and the image eventually just falls apart.
This is classic covariate shift.
Exactly.
Yeah, of course. Because the student's own predictions determine its future states, the distribution of states it visits during inference just drifts away from the distribution of states the teacher provided during offline training.
Which is why on-policy distribution matching is mandatory for high-fidelity distillation here.
Yeah.
By forcing the student to generate its own trajectories, it will naturally visit states where it's made slightly flawed choices.
Right.
But because we are querying the teachers dynamically at those specific flawed states, the student receives dense supervision on how to correct its own unique mistakes.
It learns how to recover.
It learns to recover.
Yeah.
And the empirical data in the paper proves this. On-policy distillation yields significantly better prompt adherence and visual quality than SFT or DMD.
Okay, that makes total sense. It's the difference between watching a master driver on a perfectly clear, dry drive versus having the master driver sitting in the passenger seat while you drive, and they grab the wheel to show you how to correct a slide the moment you hit a patch of ice.
That is a great way to put it. And it perfectly sets up the mathematical core of this paper. because while on-policy distillation has been, the driving force behind recent leaps in large language models.
Right, LLMs use it all the time.
Lifting that framework over to diffusion models is highly non-trivial.
Yeah, let's dig into that math translation, because in LLMs, the architecture makes OPD relatively straightforward. You're dealing with a discrete vocabulary, maybe 50,000 tokens. Calculating the reverse KL divergence between the student's next token distribution and the teacher's next token distribution, it just requires summing up the probabilities over that discrete vocabulary.
It's just a big sum.
But diffusion models don't output discrete tokens. They operate in continuous pixel or latent spaces.
Right. We're dealing with flow matching models that discretize a reverse time stochastic differential equation, an SDE. When you were running a reverse time SDE to denoise an image, you can't calculate continuous time perfectly. You have to chop it up into discrete time steps using numerical solvers, like the Euler-Maruyama method.
Sure, you approximate it.
That essentially approximates the continuous path step by step. But the state space at each step is still a continuous vector, not a discrete list of words.
Right.
So the challenge the authors faced was, how do you calculate a closed form per step KL divergence between a student and a teacher in a continuous space without the math just exploding?
And this is where we hit the absolute aha moment of the paper.
It is a beautiful piece of mathematical insight. The researchers modeled that single Euler-Maruyama SDE step as a one-step Gaussian transition kernel.
Okay, track with me here.
Now, think about how the on-policy distillation is structured. The student is rolling out the trajectory. So at any given time step t, both the student and the teacher are looking at the exact same noisy latent state.
Right.
Furthermore, they're both subject to the exact same noise scheduler and the exact same global noise level for that time step.
Wait, let me think about the implications of that for a second. If the global noise level and the scheduler are identical for both models at time step t, that means the variance injected into the process at that step is fixed, which means their transition kernels share the exact same covariance matrix.
Yes. The variance is entirely dependent on the environment, the scheduler, not the models themselves.
Wow.
So you have two Gaussian distributions representing the student's prediction and the teacher's prediction. And because they share identical covariance, they only differ in their means.
Just the means.
Just the means. The mean simply represents their predicted velocity, meaning how they want to push the latent vector to remove the noise.
Okay, let's bring back that driving analogy to visualize this. You have two drivers, the student and the teacher, navigating the exact same patch of black ice.
Right.
The environmental condition, the specific slickness of the ice, the noise, is mathematically identical for both of them. Because those complex environmental variables are perfectly shared, we don't need to calculate the massive probability distribution of the environment itself to see who's driving better. We just need to look at how differently they are turning the steering wheel.
The turning of the wheel is the transition mean. And mathematically, when you calculate the KL divergence between two Gaussians with identical covariance, all the complex, intractable stochastic noise terms analytically cancel out.
They just disappear.
They just disappear from the equation. The entire KL divergence collapses into a simple closed form L2 distance between the student's transition mean and the teacher's transition mean.
It just becomes a mean squared error loss between two vectors.
Yes.
That is incredibly elegant. You don't need any Monte Carlo estimation to approximate the variance. You just measure the distance between the two velocities.
And that mathematical collapse is the secret weapon of DiffusionOPD. That closed form objective is what allows this method to bypass the massive variance traps that standard reinforcement learning approaches like PPO just get completely stuck in.
So the math looks incredibly clean on the whiteboard.
It does.
But how does that actually solve the variance problem in practice? Why is this closed form KL vastly superior to just treating the teacher as a reward model and optimizing the student with PPO?
To understand that, we really have to look at PPO's fatal flaw in continuous spaces. Let's assume you do exactly that. You treat your perfect teacher model as a process reward model that evaluates every step the student takes.
Okay.
To optimize the student, to maximize that reward using a PPO-style policy gradient, you have to use the score function estimator.
Right, because PPO optimizes the log probability of the policy.
Exactly. The score function relies on taking the gradient of the log probability.
Yeah.
In a Gaussian policy, that log probability term expands into a quadratic equation that inherently includes the random noise variable epsilon.
All right.
When you differentiate it, you are left with a term that is directly proportional to that random noise.
So your gradient update is literally being multiplied by the random noise sampled at that time step.
Yes. So even though PPO is unbiased in expectation, meaning if you ran infinite samples, the gradient would eventually point in the right direction.
But we don't have infinite compute.
Exactly. The gradient you get on any single training step is wildly noisy. If epsilon happens to be large, your gradient explodes in a random direction.
Wow.
You are injecting massive variance into your optimization process simply because of the foundational math PPO relies on.
Which explains why PPO requires such massive batch sizes and just endless hyperparameter tuning to stabilize in diffusion models.
Yep.
But with the closed-form KL objective, we bypass the score function entirely.
Entirely. Because the distance is collapsed into an L2 loss between the means, you don't need to sample probabilities. It allows for standard pathwise backpropagation.
Nice.
You are taking the exact direct derivative of the transition mean with respect to the model parameters. The gradients are clean, stable, and highly informative at every single step, pointing exactly toward the teacher's optimal velocity.
And there is another massive win for ML engineers here regarding sampler.
Oh, yeah.
PPO, by definition, requires a stochastic policy. It needs those probability densities to calculate the log probabilities, which means it absolutely cannot handle deterministic ODE samplers.
Which is a severe limitation. ODE samples like DDM or Euler, they're highly desirable in production because they don't inject random noise at each step.
Right, they allow for much faster, more consistent generation with fewer steps.
Exactly. But PPO breaks if you remove the noise. The closed-form KL objective, however, seamlessly transitions into the deterministic ODE regime.
How so?
Because the objective reduces entirely to matching transition means. Yeah. The ODE setting, distribution matching just gracefully becomes direct transition matching.
So you completely strip out the noise requirements. Nebulation studies in the paper really highlight what a game changer this is. They show that distilling using an ODE sampler with zero added noise is up to 5 times more efficient than using a high noise SDE sampler.
5 times.
5 times. That is a monumental saving in compute overhead for any team trying to train these models.
It is a massive reduction in GPU hours. And that efficiency translates directly to the empirical triumphs of the paper. It's not just about mathematical elegance,
Yeah.
It's about what this architecture actually produces when you run the benchmarks.
Let's examine those empirical results. Does this actually solve the multitask bottleneck we discussed at the start? Like, how much better does DiffusionOPD perform against the baselines?
Across the board, DiffusionOPD outperforms the multitask baselines. They tested it against multicast GRPO guard and Cascade NFT across 3 distinct metrics.
Okay.
GenEval for compositional alignment, OCR for text rendering accuracy, and PIC-score for aesthetics. DiffusionOPD achieves state-of-the-art on all of them. But what you really want to look at are the convergence curves.
Right, the actual GPU hours required to hit those scores.
Right. If you look at the multitask RL baselines, they take well over 130 GPU hours just to slowly grind their way up to a suboptimal score.
That's the gradient conflict.
Exactly. The model is taking 1 step forward on aesthetics and half a step backward on composition. But DiffusionOPD, combining both the time to train the independent teachers and the distillation phase, requires significantly fewer GPU hours. We are talking under 100 hours total to hit a much higher performance ceiling.
The efficiency is undeniable, but as we know with text-image models, seeing is believing.
Always.
Let's actually analyze the visual case studies they provide because they perfectly illustrate the failures of the previous paradigms. The first prompt they highlight is Google Research Pizza Cafe.
This is a classic stress test for combining aesthetics and text rendering.
Yeah.
If you look at the single task GenEval teacher, it completely fails the text rendering. It misspells the sign wildly because it was only trained on composition.
Right.
The multitask RL baselines manage to get the text mostly right, but the images suffer from that task difficulty imbalance we talked about. The lighting is flat, and the storefront just looks, well, artificial.
But DiffusionOPD.
DiffusionOPD renders a gorgeous, highly aesthetic storefront with rich lighting, and the text Google Research Pizza Cafe is rendered flawlessly on the awning. It seamlessly merges the aesthetic teacher's style with the OCR teacher's accuracy.
Then they run the compositional stress tests from GenEval. The prompts are a zebra underneath a broccoli and a giraffe underneath a microwave.
I love these prompts.
They're so weird. But they're specifically designed to be bizarre, out-of-distribution concepts to ensure the model isn't just relying on memorized training data. It has to actually follow the spatial constraints.
And this is where Cascade NFT, that sequential training baseline, completely falls apart. It shows severe catastrophic forgetting.
Because it trained on aesthetics last.
Right. So it prioritizes making a pretty picture but forgets the complex spatial rules. It produces weird visual artifacts or just puts the giraffe next to the microwave, ignoring the underneath constraint entirely.
And DiffusionOPD.
DiffusionOPD produces insanely crisp, visually stunning images with flawless compositional alignment. You literally have a giant, highly detailed piece of broccoli floating perfectly over a realistic zebra.
It's absurd to look at, but it proves the point perfectly. My personal favorite, though, is the prompt for a 1920s airship shaped like a pig.
Oh, that image is a masterclass in multi-reward alignment. It highlights the exact failure point of single-task models.
Right, because the GenEval teacher makes a great structural composition of a pig-shaped airship, but the image itself looks like a flat, boring render, and the text painted on the side of the blimp is total gibberish.
Exactly. But DiffusionOPD gives you this rich, sepia-toned, vintage film grain, perfect structural alignment of the pig shape, and sharp, coherent details. It takes the absolute best traits of all three teachers and harmonizes them without compromising on any single axis.
So synthesizing all of this, what is the ultimate takeaway for the ML community out there listening?
Ultimately, DiffusionOPD provides a highly scalable, mathematically stable framework for model building. It proves that you don't have to fight through the high variance mud of multi-reward PPO tuning, and you don't have to navigate the catastrophic forgetting of sequential training.
You just bypass it.
Right. By structurally decoupling exploration from integration and utilizing a low-variance closed-form KL objective, you can build a single unified model out of highly specialized experts. It fundamentally lowers the barrier, both mathematically and computationally, to training complex, multi-capable diffusion models.
Which leaves us with a pretty provocative implication to consider.
Oh, definitely.
If you can seamlessly distill distinct, specialized diffusion teachers into one student without their gradients fighting,
Yeah.
what happens when we scale this up? Could a team train hundreds of micro-teachers on hyper-niche tasks, say, one model just for rendering human hands perfectly, one just for cinematic lighting, one trained exclusively on rendering specific brand logos?
And then effortlessly compile them all into a single foundational model.
Exactly. Is the future of AI training moving away from giant, monolithic, multitask runs and moving toward assembling a perfectly distilled team of narrow experts? It is definitely something to think about.
It really changes the whole paradigm.
It does. Well, thanks for joining us for this deep dive into the paper. We'll see you next time on AI Paper Slot.